This is a lesson on electric potential energy in a unit on electrostatics. I wanted to start us out with just a quick review of some fundamental principles in physics that will be relevant for this lesson and the next. The work done by a force, we know, is dependent on the force and the distance that force acts over. And depending on the force, if you have a constant force, you can just use F(d) cosine theta. But with electric forces, we often don't have a constant force. So calculating the work done by an electric force is going to be a little bit more complicated, which is why we're looking at electric potential energy. We've already looked at different types of energy in prior physics courses. There's translational kinetic energy that will be a type that's relevant for us. And I also wanted to bring up gravitational potential energy because gravitational potential energy and electric potential energy are very analogous to me. We'll explore that idea more as we move forward. Finally, conservation of energy. You can see that I have a very, very general situation here in terms of states. There's an initial energy state, and then we have some sort of energy in or out of a system, and it will equal some final energy state. This arises from the work kinetic energy theorem, but I prefer this one because it is more thinking about states in terms of the state functions and easier to use in word problems. So I'm going to hold on to this as we move through this lesson. Another review to go over is the idea of electric potential, which is different than electric potential energy. Electric potential is defined as the capacity of an electric field to do work on a charge if a charge were present. Electric field lines point from high to low potential. This is analogous to what we see with gravitational potential energy. When I think about gravitational potential energy, G, 2 over R, I have two masses. The gravitational field lines will point in the direction of high potential to low potential. So positive charges move along the electric field lines and they will move from high to low potential. So it's like positive charges fall in an electric field, whereas negative charges move from low to high potential and they rise in an electric field. So that's an oddity, and we'll keep that in mind as we think about electric potential energy. Is a charge gaining energy or losing energy? Which direction do we expect them to move in the electric field? We'll keep all that in mind. So electric potential energy is an energy associated with the position of a charge in an electric field. And this is true for any potential energy we look at. Gravitational potential energy depends on position. Elastic potential energy depends on position. These potential energies depend on the position. It's an energy of position. The energy associated with a charge in an electric field depends on the charge and the value of the voltage at that location. So not only, is it dependent on the position, we can say that there's a voltage at a location. Electric potential energy is Q times V, just the charge times the voltage. Super easy equation, very easy to use. And we can see that the electric potential due to a constant electric field or the electric potential due to a point charge can both go into this equation. Due to a constant electric field, it's the ED equation. Due to a point charge, it's KQ over R. And you could, whatever situation you're in, you can plug those expressions in for V in this equation, and you would have an expression for the electric potential energy for a charge in an electric field, and you know the voltage. The advantage of electric potential energy is I don't have to think about the work done by an electric field. I can just think about the initial energy state of a charged particle and a final energy state of a charged particle, and if that charged particle has potential energy in the initial or final state. So again, we're looking at the conservation of energy in the state form that I like to use, and that's how we're going to use it, is where do these charges have electric potential energy? So when I think about this a little bit more deeply, right, the conservation of energy with electric potential energy, here I have an electric field, and you can see the analogy of gravitational potential down here. When I have a mass, the mass will naturally move down a hill. It will naturally move from a region of high gravitational potential to low gravitational potential. And we see that with a positive charge. A positive charge, when we're close to positive plates, when we're close to a positive charge, this is going to be high potential. And we move to a negative charge, this is going to be low potential. And so when we look at this charge in this electric field, it has some sort of electric potential energy associated with this position in the electric field. When it moves to the other side, it's going to have some sort of final potential energy, and it will have a kinetic energy. Of course, it's sped up. The electric field has accelerated it through there. It started at rest, so it would have some initial kinetic energy at 0, and it accelerates through there. And that's often how we actually accelerate charges. So when we use it, it can be used as another potential energy term. And so I wrote that out here. The initial kinetic energy would often be 0 if it starts from rest. It has some sort of initial electric potential energy, which we'd be able to calculate. You'd have to figure out if there's work in or out, but typically there's not. We're just dealing with conservative fields and often just changing electric potential energy into final kinetic energy. And we can see that in this situation. The final voltage at a negative charge will be 0, and it will have some sort of final kinetic energy, and you'd be able to calculate, you would be able to relate those two values. So our strategy is to think in terms of form of energy in the initial state and in the final state, and use this equation in order to set ourselves up to solve problems. Of course, I have a quick example here, a pretty basic example, speeding up a proton. It says calculate the final speed of a free proton accelerated from rest through a potential difference of 150 volts. And so we know that electric potential energy is Q times V. It seems if it's a proton and there's some sort of potential difference, there's going to be a region of high potential over here, which we can represent with positive charges, and then we'll have low potential, which is negative charges. And obviously this proton is going to want to move away from the positive charges and move towards the negative charges. So it's moving from high potential to low potential. Okay, so it's going to start out with some initial potential energy and no kinetic energy. It says it starts from rest, so it has no kinetic energy, and it starts with some sort of initial potential energy, which I'm going to put Q V initial in here. There's no work by other forces in here, it's just the electric field, and at the end it's going to have some sort of final kinetic energy, which I'm going to represent as 1/2 mv squared. We want to find the final speed, so we'll be solving for V. And the final potential energy, the final electric potential energy, well, it says it goes through a change here, a change in voltage of 150 volts. So what I'm saying is it's 150 here and 0 here. That may not actually be the case, but generally in a constant electric field, it will have a voltage of 0 near the negative charges. So we have a plus 0 here, that's a 0. So when I look at this, I just have a very simple equation to solve. I'll solve this equation for V. The speed is going to be 2Q times that initial voltage over the mass of the proton, and I'm going to have to remember to take the square root too. I'm going to highlight in this situation, if you were still using a small v for velocity and a big V for voltage, you may want to exaggerate their sizes so you don't confuse them in your equation. But that's the reason I use a script V, is so that I don't have to be so particular when I write V for voltage. So script V is the speed. And when I plug numbers in here, I'm going to get 2 times the charge of a proton, 1.6 times 10 to the negative 19th. The voltage, 150, and the mass of a proton is 1.6729 times 10 to the negative 27th kilograms. As long as all of those are in SI, I wouldn't worry about the units too much, but you may check them just to be sure for yourself. And when you run this through your calculator, you get 169,389 meters per second. And I rounded that off to 170 kilometers per second. So that's not like a large velocity for a proton, but we can get a proton moving pretty fast through a potential difference. If we want to find the electric potential of a point charge, we can plug in what we know about the potential of a point charge into the electric potential energy equation. So we get Q times KQ over R, and I know when you look at that, you're going to get Q naught KQ over R, but we change this to be represented with two charges, Q1 and Q2, and that's very similar to what we know about gravitational potential energy, the universal gravitational potential energy, M1 and M2. We just put in there Q1, Q2 over R. So you could find the electric potential energy of just 2-point charges. If you want the electric potential energy of a charge in a constant electric field, so let's create a situation where there's a constant electric field. There's some voltage here and some voltage here, V1 and V2. So electric potential energy is Q times the voltage. When I have a constant electric field, that change in voltage is going to be the ED equation. So I can just plug that in here. And for a constant electric field, not for the point charges, but just for a constant electric field, you get the electric potential energy to be Q times E times D. And you could also use that in situations, and that would be better represented in the situation that I had earlier here, where I might have... where I might know the value of this electric field and I might know the distance between these two plates, and then I would be able to find the potential difference between those two plates, delta V equals ED. And you could use that in this equation here. Q times E times D would be that initial potential energy of that charge in the electric field.